In this video, I'm going to show you the acetoacetic ester synthesis. Quite a big name for this reaction, but it's really not all that complicated. But there are 4 basic ideas behind it. We're going to look at where the name comes from, those 4 basic ideas, and then you'll understand how this reaction proceeds. Let's jump right in. Here's where the name comes from. A methyl on a carbonyl is an aceto group. So if I made the carboxylic acid out of this, that would be acetic acid. So if I put this aceto group on this acetic acid, I would get aceto acetic acid. And the ester of this carboxylic acid, acetic acid ester. So acetoacetic ester synthesis means we're just going to use that to make some new things. So the acetoacetic ester synthesis. That's where the name comes from. All right, let's see the 4 basic things you need to know. Number 1, if I react this with a base, we know that bases pull off acidic protons. And we know that if we have carbonyls, carbons next to those carbonyls, alpha carbons, have acidic protons on them. So here's a carbonyl. There's an alpha carbon with acidic protons. I could pull those off. Here's carbonyls with an alpha carbon and protons. I can pull those off. And there's not one here. So if I pull one of these off, I would make a negative carbon like this. And we would like to pull those off because those negative electrons can be pushed up to that oxygen. And I can share that negative charge on this carbon and this oxygen. I share it on 2 atoms. That makes it happier than all alone on one. But what if instead I pulled off that hydrogen? Well, that would make this negative charge. And that negative charge is very stable because I can push the electrons up to that oxygen or this oxygen. So I share that negative charge over 3 atoms, which makes it super stable, super happy. So therefore, anytime I have hydrogens on a carbon between 2 carbonyls, that's where we're going to pull off the proton. Idea number 1. Idea number 2, if I have a negative carbon, it could backside attack something with a good leaving group like a bromide. If it's not too crowded, so a primary alkyl halide like this would work well, I could backside attack, the leaving group could leave SN2 style, and that carbon could attach to other carbons. Idea number 3. We have previously seen that carboxylic acids react with alcohols with acid present to undergo a Fischer esterification, where we lose water and we make esters, R, C double bond O, O, R prime. And water falls off. So if I distill away the water, I can make more and more of this ester. But this is an equilibrium reaction, and we haven't talked yet about going backwards. So in an ester like this, if I add a bunch of water, and acids around, I can make it go. So if I have acid and water and some heat, I can hydrolyze this ester and make carboxylic acids back out of it. I could break it apart, add the water, and break that bond. So esters with acid and water, they can hydrolyze to make carboxylic acids. Number 4, if we have a carboxylic acid, and it is 2 carbons away, my carboxylic acid is alpha, beta, to another carbonyl, we can do a reaction called a decarboxylation. It can decarboxylate. That means you lose carbon dioxide. Let me show you where the carbon dioxide is hidden. It's right here. There's a CO2, carbon dioxide. So, if a carboxylic acid is alpha beta to a carbonyl, it doesn't matter if it's a ketone, an aldehyde, a carboxylic acid, any carbonyl on the beta spot, you lose the carbon dioxide. We're just going to cover up the CO2 and draw what we get, what we make. So now this hydrogen's on this carbon, the carbonyl and our group. We decarboxylate, lose the carbon dioxide. Now that we know those four things, let's look at our acetoacetic ester synthesis. Acetoacetic acid synthesis, ester. Okay, there we go. Step 1, we had base. Ah yes, we remember, between the two carbonyls, that's the most acidic hydrogen. So the base will pull off one of these, leave the electrons behind to make methyl, carbonyl, carbon with one hydrogen, a lone pair and a negative charge, to carbonyl, OET. Step 2, we're going to do an SN2 style reaction, and these enolates can do that. So let's add propyl with a good leaving group, propyl bromide. We backside attack, leaving group leaves. And there's one hydrogen and a propyl on there now. Step 3, we're going to add acid, water, and heat it up. We're going to hydrolyze this ester. So now we have CH3, C double bond O, my hydrogen and propyl, and the ester becomes the carboxylic acid. Kind of the backwards version of a Fischer esterification. Anytime we see a carboxylic acid, I want to know, will it lose carbon dioxide? Well, let's see. It's alpha, beta to a carbonyl. Aha! Yes, I will lose the carbon dioxide. So we cover up the CO2, and that's what we're going to draw. So that makes methyl, carbonyl, a hydrogen there, boop, boop, boop. I cover up my CO2, and that hydrogen is on this carbon. And that's the final product of the acetoacetic ester synthesis. Here's where all the pieces come from my final product. That methyl, that carbonyl, and that carbon come from these parts. And this propyl comes from that propyl. And I lost this part because I turned it into a carboxylic acid and decarboxylated. So that part I'm going to lose in the end, and I can put whatever group I want to on that carbon to make my final product. Make sure you understand those four basic ideas, and if somebody gives you the reagents, you should be able to walk through the acetoacetic ester synthesis. Hey, please subscribe to the channel because I don't want you to miss any of my upcoming videos because I want to be able to help you with organic chemistry.